Hello, this topic will be all about matrices. So, we'll first go to the terminologies. So, matrix is denoted as A equals the matrix with elements A sub ij, which is a rectangular array of numbers with m rows and n columns, which can be represented this way. You can think of this as the 2D arrays that you have learned in CCDSTRU 2. So we have here the ith row of the matrix and the jth column of the matrix. So in programming, specifically in C, you may have been familiar that this first element or the index would always start at 0 for rows and as well as for columns. So for matrices in mathematics, you would start with index 1 for both row and column and end up to some specified size for the number of columns and rows that you have for the matrix. So now we will proceed with the matrix operations. So here we have matrix addition. It is an n by n matrix where A and B are both m by n matrices. So when you apply matrix addition, you need to make sure that both matrices that you are adding are the same in dimension with regards to row and column. So if we have something like let's say this is the first matrix plus another matrix, say 5, 1, 1, 1, it would result to 1 plus 5, 6, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. Notice how I'm adding them based on the same row and column that the elements have. So this one is A sub 2 over 2, and this one, let's say, is B sub 2 over 2. So I'm basically adding them to get this value, which is A sub 2, 2, plus B sub 2, 2, and then this, and so on and so forth. So you can also see it here that whatever you're adding would result in the same row and column as those of the elements in the matrices that you are adding. Next, we have scalar multiplication, which is an n by n matrix where C times A is equal to C times A sub ij, and C is a real number. So here, you're actually applying basically any real number to every element in the matrix. So if I have something like 5 times, let's say, this matrix over here, if I multiply 5 to the matrix A, let's call this matrix A, then we need to apply multiplication across all elements of the matrix. So with that, our result would be to multiply 5 to each element. So that would be 5, 5, 0, 0, 5, 15, and 0, 0, 10. And that would be for scalar multiplication. Now, before we proceed with the next operation, subtraction is not a defined operation in matrix multiplication. That is because we only have 2 operations that we have defined so far, which can actually be used to sort of create subtraction of matrices. So if we have a matrix A and a matrix B and you want to subtract them, the longer way of actually defining scalar multiplication is to have a matrix, apply matrix addition, then apply scalar multiplication to the matrix B by adding multiplying -1 to all elements, which should result to A minus B. So next, we have matrix multiplication, which is an n by n matrix where A is an M by K matrix and B is a K by N matrix. Each term C sub ij is formally defined as follows, which is the summation of all elements A sub ix times B sub xj from x equals 1 to k. So this may be confusing at first, but here we can show in the following slides a simulation on how matrix multiplication works. So first, we will define first our matrices that we will use for matrix multiplication. So here we have A, which is a 3 by 3 matrix. B is a 3 by 2 matrix, which means our product AB is a 3 by 2 matrix. Why is that so? Again, 3 as matrix A is 3 by 3, and our matrix B is 3 by 2. And based on our definition a while ago, to get the product of two matrices, you need to first satisfy that the first matrix is dimensions m by k, and the second matrix has dimensions k by n. So we need to make sure that the k, or the number of columns of matrix A and the number of rows of matrix B are equal and should be the same for matrix multiplication to work. And with that, the resulting matrix would be 3 by 2, which results to the m by n matrix. So if I have, let's say, a 5 by 8 matrix, and I have an 8 by 1 matrix, my resulting matrix would be 5 by 1. If I have, let's say, a 3 by 1 matrix, and then I also have another 1 by 1 matrix, let's change the color. The resulting matrix would be 3 by 1. And if I have, let's say, a 1 by 10 matrix, and then I also have another 10 by, let's say, 7 matrix, my resulting matrix would be 1 by 7 matrix. So we need to make sure that your k over here must be equal at all times. Hopefully that clears up how matrix multiplication would work in terms of its dimensions. So now let's proceed with the actual matrix multiplication over here. So first, when we get the first element, C sub 1, 1, again, we need to follow that we are doing the summation from 1 to k of A sub I x and B sub xj, and applying their product. So here, we are already multiplying A sub 1, 1 and B sub 1, 1. And then, we are adding it to the next set of things to multiply, which is A sub 1, 2 and B sub 2, 1. And then lastly, A sub 1, 3 and B sub 3, 1. Notice how the x here, which is the column of row of element A and the row of element B, are the same. So these are the same, these are also equal, and these ones are also equal. And that must be satisfied to get the product, the sum of the products of both matrices to get the first element C sub 1, 1. And that's only for the first element of the product matrix. So matrix multiplication is very tedious, but with enough practice, you would get used to it. So for the next term, which is C sub 1, 2, again, apply as follows. A sub 1, 1 and B sub 1, 2. Multiply A sub 1, 2 and B sub 2, 2. And A sub 1, 3 and B sub 3. And then I'll leave it here to help you see how to multiply the next following terms. For C21, you have the first term, second term, and third term. For C sub 22, we have the following. And then we have C sub 31. And lastly, for C sub 32. So that is how matrix multiplication works. So notice how this one moves first. So let's go back to the very first item. Okay. So for element 1, 1, you're getting this row, and this column. And then for the next one, you're getting this row, this column next. Then once you're done with that column, you proceed to the next set of rows and columns, and so on and so forth. So you can actually sort of make an algorithm or create a program in C that takes in two 2D matrices or arrays and get the product of the said matrix. So now let's go to the actual example. So here we have A, which is a 1 by 3 matrix, and B, which is a 3 by 2 matrix, and you're asked to find for the product matrix. So first, we need to find for the dimension of the product matrix to help you be guided on finding out the elements of the product matrix. So since A is 1 by 3 and B is 3 by 2, therefore the product matrix AB would be 1 by 2. And then here, we compute for the values of each matrix. So we are basically multiplying we're getting the sum of the products of the elements of both matrices A and B. So we start with 5 by 1 first, plus 4 times 3, plus 0 times 4. And then we have the next element, which is 5 by 2, 5 times 2 rather, 4 plus 4 times 2, plus 0 times 2. And this is what we would have as of the moment. So when you add them to add these terms, you'd get 5 plus 12 plus 0, which is 17. And then 10 plus 8 plus 0 equals 18. Therefore, the product matrix would be a 1 by 2 matrix consisting of elements 17 and 18. So now we have different kinds of matrices that you will encounter. First is the identity matrix, which is an n by n square matrix, I sub n equals delta ij, where delta I sub ij equals 1 if I is equal to j, and 0 if I is not equal to j, which basically is a square matrix where the diagonal is mainly full of ones. So if you have a square matrix over here, only the diagonals would have ones, and the rest would just be 0. So everything else would be 0 except for the diagonal. Another thing that is interesting about identity matrices is if you have some matrix A, which is, let's say, it has dimensions m by n, and then your identity matrix I sub n is n by n, your identity matrix product would be m by n. And in fact, if your matrix is a square matrix, let's make this n instead. When you multiply A times an identity matrix, you'd still get the same matrix. That is up to you to find to sort of play around with to determine whether this is true or not. So next we have the transpose matrix. So this is an n by n matrix, a sub a raised to t, which is equal to a sub ji, where the original is an m by n matrix, a equals to a sub ij, for I equals 1 to m and j equals from 1 to n. So with this, you can think of your transpose matrix as follows. If this is your original matrix, this is going to be your transpose matrix. And you're sort of flipping it across this diagonal, where the elements in the diagonal will stay at as is, because the row and columns are still the same value even if you flip them, so it won't make much of a change. Meanwhile, for the other elements, elements that go here will go here and vice versa. And then elements that go here would also go there, and elements that go here, actually, yeah, elements that go here would go there. And if you're starting with this blue matrix, then elements that go over here would go here, and here would go here. Then if you have a square matrix, if you have a 3 by 3 matrix, then your transpose would also be 3 by 3. And the only thing that would change is the elements in here, like so. And again, the diagonals would not change in terms of value. So let's have an example. Given this matrix A, find the transpose. So first, find the dimension of the transpose matrix. Since we have a matrix that is 3 by 2 in dimension, therefore the transpose is 2 by 3. Then we construct the transpose matrix. So how did we derive to this answer? So again, your A sub ij becomes A sub ji. So if this is your original matrix, 1, 2, 3, 5, 9, 7, we'll keep the diagonal elements in place. So this is 1 and 5. This is, now we focus on the other elements. So here, 2 over here is originally A sub 1, 2. We swap it and we turn it into A sub 2, 1. And that would be falling under here. And then 3 is A sub 2, 1, which would become A sub 1, 2, which would fall under here. Because this is, let's put it here. This one is row 1, no, column 1, column 2, column 3. Then this one is row 1, row 2. Okay, then 5 will and 1 will stay in put because A sub 1, 1 is just the same as A sub 1, 1. Then A sub 2, 2, swap it, it's still A sub 2. So, stay put lang yung elements in the diagonal. Then we continue with the others. A sub 9 over, not A sub 9. Element 9, which is A sub 3, 1, becomes A sub 1, 3. So that would fall in row 1, column 3, which is over here. And then lastly, 7, which is A sub 3, 2, would become A sub 2, 3, which would fall under here, row 2, column 3. So that would be your transpose matrix. So essentially, you're flipping only the values of the rows and columns of each element, which would help you create the transpose matrix. So now we have another example over here. This time is a square matrix. And again, as I said a while ago, if a matrix is a square matrix, the transpose matrix would have the same dimensions. And if we construct a transpose matrix, we would get this. And again, following the rule of transpose matrices, A sub ij, the original one, would swap the row and element as your new row and column for the transpose matrix. So 1, 2, and 10 stay put, as you can see over here. Then 3 and 2 swap places, 3 and 12 rather. 11 and 0 swap places. And 4 and 7 swap places. Because, let's say 3, which is A sub 1, 2, would become, no, I'm so sorry. I'm looking at the transpose matrix. So A, which has 3 over here at A sub 2, 1, becomes A sub 1, 2. 12, on the other hand, from A sub 1, 2, becomes A sub 2, 1. And so on and so forth for 11, 0, 4, and 7 here in the transpose matrix. Then we have a symmetric matrix, which is a square matrix A that is equal to all its transpose counterpart, where A sub ij is equal to A sub ji for all I and j, where I is from 1 to n and j is from 1 to n. So, for it to be a transpose matrix, it needs to be first a square matrix. And a sample of this would be the identity matrix. Because, again, only its diagonal has 1 and then the rest are just zeros. If the said row and column are not equal, meaning they are not on the diagonal. So, if we take the transpose of an identity matrix, you're still getting the same matrix. So that's an example of a symmetric matrix. Another example would be, let's say 1, 1, 1, 5, 5, 2, 2, 3, 3. Or let's say 1, 0, 7, 2, 2, 10, 10, and 3, 3. That's also another example of a symmetric matrix, because if you get the transpose, you'd still get the same answer. So that is for symmetric matrices. So now we have the power of a square matrix, which is a square matrix A sub n, A raised to n, which is the matrix multiplied to itself n times. So if you have, let's say, a matrix like this, and you want to get A squared, you'd have to do matrix multiplication to itself and do the necessary operations to get to your answer. So that would be 2, 1, 1 times itself. So we start again from here, then here. So that would be 2 times 2, 4, plus 1 times 1, 1. So that's 5, plus 1 times 1 is 6. And then 2 times 1 is 2. Then, so that's 2 times 1, 1 times 2, plus 1 times 1, which is 4 plus 4 equals 5. And then here again, so that's 2 times 1, 2, plus 1 times 1 is 1. So that's 2 plus 1, 3, plus 0, which is equal to 3. And then so on and so forth. So we'll just continue this. 1, and then 2 again, So that's 1 times 2, 2 plus 2 plus 1, 5. Then here again, with this row, so that's 1 times 4 plus 4 plus 1. So that's 6. And then 1 plus 2 is also 3. And then lastly, 1, no, this is 2. We're now in this row. So this is 1 times 2, 2. Plus 1 times 1 is 1. Times 0 times 1 would be 2 plus 1, 3. Then the next row is 1 times 1, 1 times 2, and then 0 times 1. So that is also 3. Lastly, that's 1 times 1 plus 1 times 1, which is 2. Plus 0 equals 0. And this is your matrix. Notice also that it is a symmetric matrix. But that is not the case always for power of a square matrix, because based on my example over here, it's already symmetric and our result is still symmetric. You can play around it with other matrices as long as they are a square matrix, because if it's not a square matrix, if A is, let's say, m by n, and if you multiply that to another m by n matrix, these are not equal, so therefore you cannot make a product matrix out of it to begin with. So that is for square matrices, which can go to a sub raised to 2, a raised to 3, and so on and so forth. So here are some exercises regarding matrix operations. So given the following matrices, evaluate the following. And there are no answers for this, but you can try for yourself and see if you are correct, especially with those with matrix multiplication, which is the difficult one, alongside transpose of a matrix, which is just as difficult as matrix multiplication. So please try these out. Now we go to the 0-1 matrices. A 0-1 matrix is an m by n matrix whose entries are only 0 or 1. So basically, it's like an array containing true or false values. So it can be something like this. It does not necessarily have to be like an identity matrix. It depends on what you are computing for. So this is an example of a 0-1 matrix. So now we have the matrix operations for 0-1 matrices. First is the meet of a matrix, which is a 0-1 matrix where A and B are both 0-1 matrices of the same dimension, where A sub ij and B sub ij is equal to 1 if and only if A sub ij is equal to B sub ij equals 1 and 0 if otherwise. So going back to propositional logic, the very first topic in CCDSTRU, you know that if you have two propositions and if you have their truth values, let's say this one's true, false, false, true, false, true, false, P and Q will result to true if and only if both are true, and the rest would be false. Similarly, 1 and 1 would be equal to 1, and then for other terms in the matrix, 0 and 1, 1 and 0, or 0 and 0 are all equal to 0. And again, like matrix addition, you do this element-wise. So you apply this to this on the same operation and get this one. And then like, let's say A sub n meeting B sub mn would get the result over here. And then we have its counterpart. the join of a matrix, where like the meat of a matrix, it has the same specifications. It's an m by n 0, 1 matrix where A and B are both also 0, 1 matrices of the same dimension, m by n, where A sub ij or B sub ij is equal to 0 if both A sub ij and B sub ij 0 and 1 if otherwise. Again, if you have P and Q over here, and then we take the disjunction of two propositions, applying the truth values as follows, you know that if it's OR, it would be true if either one of the statements are true and false if both statements are false. Similarly, if you have 1 or 1, 0 or 1, 1 or 0, you'd get 1 for all values, and if it's 0 equals 0, 0 or 0, then you'll get 0. And like matrix addition and the join of a meet of a matrix, you do this element-wise in terms of applying the operations. And then we have the Boolean product, which is an m by n matrix, where A is an m by k matrix and B is a k by n matrix, which each term C sub ij, which is the third element of a product, not product matrix, Boolean product is formally defined as follows. So, if you're wondering what this symbol means, it's similar to sigma, where you are adding terms, and for this operation, you are taking the disjunction of multiple elements. There's also one for and there are also other large operations which you may not have seen yet before in CCDSTRU, like the union, where you take the union of multiple sets, intersection, where you take the intersection of multiple sets, and then you also have product, which is taking the product of multiple terms, which can be like from some specified value. Like how you do it in summations, it also has a lower limit and upper limit, and your the terms that you will be evaluating within the operation. So in this case, this is equal to let's say if k is equal to 2, this would be equal to a sub 1, 1, and b sub 1, 1. No. But to put it short, it's basically getting the OR of all terms by applying the meet of a matrix and then applying the join for every term. So example in here, you're taking the a sub 1, 1 and b sub 1, 1, and then taking the or the disjunction until you reach the value k, and so on and so forth. It also functions similar to a product matrix. So if you want to figure out how this applies, look back to the matrix multiplication simulation and replace the plus sign with or, and replace the multiplication with n. So here are some exercises regarding 0, 1 matrices. So given the following three matrices, evaluate the meet, join, and Boolean product of the following matrices. And that is all for matrices.